295, discussing stoichiometry and chemical formulas and how we use stoichiometry to determine chemical formulas. And I'll leave it to you to read the bottom of 295 and 296, because at the bottom of the paragraphs there they say, you know, this whole concept will get a lot easier when you see the example. They basically put it off to the example to teach the subject to you. So we're going to jump right to the example as well. Example A8. It says that a chemist decomposes an unknown compound. So from that right there, I know that I'm going to have a reaction. With the reaction arrow, I'm expecting to have a molecule on this side, right? It's decomposing. So I'm going to have a molecule on this side, and I'm going to have some, we're going to break this down into its elemental forms. So a chemist decomposes an unknown compound. The products of this decomposition are 12 grams of carbon. So now I'm going to have carbon as one of the products of reaction, right? The decomposition. Carbon and 4.04 grams of hydrogen. Kind of in the same vein that we've been talking about with stoichiometry and converting from mass to moles and moles to mass, I'm going to go ahead and write the information they also give us here, that we have 12 grams of carbon. Go ahead and write that down below. I think that's they give 2 decimal places. Yes, 12 grams of carbon and 4.04 grams of hydrogen. And the question is, what's the chemical formula of the unknown molecule? Now, I'm going to erase the question mark because we're going to fill it in real quickly here. There is a molecule that breaks down, and when it breaks down, its products are carbon and hydrogen. Whenever we did the decompositions before, after we broke it down, what did we look for? As we looked at the products, we had to make some notations, right? So what did we look for here? We know the products are carbon and hydrogen. We asked the question, are any of them good homonuclear diatomics? Is carbon a homonuclear diatomic? No. Is hydrogen? Let's note it that way, right? Because it's breaking down into its elemental form. So the products of this decomposition are carbon and hydrogen, H2. So a carbon atom and a hydrogen molecule, or at least one. We just know it in some amount. So if I know I've got carbons and hydrogens as the product of reaction, in this case a decomposition, what makes up the molecule? What must this have been made up of? Carbons and hydrogens, right? Let's go ahead and write that. Carbons and hydrogens. Now here's the deal. Though we know the molecule is made up of carbons and hydrogens because the product of decomposition are carbons and hydrogens, but we don't know the actual formula. Okay? What we do know is it's some combination of carbons and hydrogens. And so what we're going to do is, since we don't know whether it's a CH2 or C2H or C3H6 or what it is, what we're going to do is plug in the variables x and y. And what is that telling me? I have some number of carbons and some number of hydrogens, and x and y have to be equal to or greater than 1, right? Because if it was a 0, remember that concept? Imagine if I had to write down everything that I don't have. It would be an incredibly long list. We're just going to write down the things that we do have, and we're going to note it if there's more than one of them. If there was nothing here, you'd assume it was a 1. We may find out that there is only one carbon, and there may be only one hydrogen. We don't know yet. But we know for right now, while we try to investigate this to figure out how much is there, that there's some combinations of carbons and hydrogens that when they decompose, they produce carbons and hydrogens. And specifically here, 12 grams of carbon and 4.04 grams of hydrogen. So again, this is a process. This is a model that you're going to use every time. If I gave you another molecule that had 2 other elements as products of reaction, do the same thing. You come to this side, you try to build up the original molecule, but you don't know what the relationships are between the count of each of those atoms to make the molecule. So you put in the unknown variables x and y. So right now, even though you may not understand where we're going to go with this, now that you know on this side that you have a certain mass of each of these, what do you think you can do with the mass? If I told you that I had 12 grams of carbon, what's another way I can say that? Right? Think of the module we're in, was that right?
Yeah.
Okay, so not grams per mole, but if I knew grams per mole, which is a constant, right? What can I figure out? How many moles of this I have, right? Let's assume we're going back down to moles. If you want to visualize it, I've got 12 grams. I want to figure out how many moles. And I've got 4.04 grams. Let me figure out how many moles. What's another way of saying that? Carbon has an atomic mass of what? You can see it over here or in front of your book. Okay. So an atom of carbon has a mass of 12 AMU, which means that a mole of carbon has a mass of 12 grams. So I can say 12 grams another way. To have 12 grams of carbon is to have 1 mole of carbon. See that? And hydrogen has a mass of 1.01. So how many moles of hydrogen gas do I have? Try again. One of the other most common mistakes. Because this is the mass of a hydrogen atom, we're not asking how many hydrogen atoms we have, it's how many hydrogen molecules we have, right? So what is the atomic mass of a hydrogen molecule? 2.02. If one hydrogen atom is 1.01, then one hydrogen molecule is 2.02. And so we would have 4 moles of individual hydrogen atoms, but we're not looking for individual hydrogen atoms. We're looking for how many moles of hydrogen molecules, which has a mass of 2.02. And so we have 2 moles of H2. Now, here's the magic, right? Stoichiometrically then, I'm going to say over here my relationship is if 1 mole of carbon and 2 moles of H2, right? I have 1 mole and I have 2 moles. See, that's the implied 1 right there. If I have 1 mole of carbon and 2 moles of hydrogen gas, let's look over to this side. Let's balance that equation, right? Whatever we have over on this side, we have to have over on this side. So how many carbons to make up this molecule must there be? Let's assume we're working in moles. I've got 1 mole and 2 moles. What must I have on this side? Well, in terms of carbons, how many am I trying to account for? 1 mole. My X becomes a 1. And my Y. How many hydrogens am I looking for? I've got 2 moles, right? But how many hydrogens are on that side then? 4. I've got 2 moles of 2 per mole, right, of the molecule. So it's 4. So I've got 1 carbon and 4 hydrogens. In order to have 1 carbon and 4 hydrogens on that side, I must have had 1 carbon and 4 hydrogens on this side. And since it's a 1 that's always implied, I can erase that. And so my molecule was methane, CH4. And I can say that 1 mole of methane decomposes to form 1 mole of carbon and 2 moles of hydrogen gas. Because methane is also a gas, carbon's a solid, and hydrogen's a gas, not only can say that 1 mole decomposes to produce 1 mole and 2 moles, but I can also say that methane gas, 1 liter, decomposes to form 2 liters of hydrogen gas. But because it's a volume in gas, I can't make any statement about carbon because it's solid, using Gila-Sock. Okay? So all this is doing, again, is give you a number of relation or relating them. In this case, carbon, with 12 grams I have 1 mole, and with hydrogen I have 2 moles. As I look across, it means I need to account for 1 carbon and 4 hydrogens in 1 molecule, and this is the way I do that. CH4. There's not a lot more to that other than doing more examples of this. That's why I encourage you to look at the on your own and the practice problems in doing this. That is the process. But there's a wrinkle to it, like they say at the bottom of 297. The wrinkle from this, looking at methane and using the same example is, okay, let's say that this is our, we say that we can get CH4 decomposes to be this and this. But they also offer that there could be other options as well. Rather than having a CH4 molecule, let's say we had a C4H8 molecule. The C4H8, when it decomposes, what is it going to decompose into? Same stuff, right? Carbon and hydrogen. But I'm going to have way too much. I'm going to need to cut down the amount here. They offer that we need 1/2 of a mole of those. Actually, we jumped ahead. C2H8 is what they use in the book. C2H8, that makes more sense because 1/2 of a C2, if I got 1/2 mole of C2, that means I've got 1 mole of carbon, right? If I've got 2 molecules per mole of this compound, 1/2 and the 2 means I'm going to have a 1, and the 1/2 times 8 means I'm going to have a 4. You see, it's the same. You'd have the same amount. If you had 1/2 mole of this, it breaks down to be the same as a whole mole of this, and they take it 1 more, C3H12. And if I had 1/3 of a mole of C3H12, it would also break down into 1 mole of carbon and 2 moles of hydrogen gas. Okay. So this is the wrinkle in using this process, is the difference between what we're going to call the empirical formula and the molecular formula. But the empirical formula, you can see the definitions on page 298, it says that a molecular formula is a formula that provides the number of each atom in a molecule. So what we've been using up to this point has been the molecular formula. What is the molecular formula of methane? It's CH4. That tells me that I have 1 carbon for every 4 hydrogens. In this case, what's the molecular formula? C2H8. In this case, C3H12. That's the molecular formula. It tells me exactly how to build up that molecule. Pulling from the parts bin, sticking stuff together, I have a formula to build up that molecule, and this tells me how many parts I need in the molecular formula. The other one is the empirical formula. And the empirical formula is what we determine using this. We do an experiment. So empirically, we do the experiment and we discover something. And what do we discover? Well, in this case, what we've discovered is that whatever it is over here we have, when it breaks down into a relationship of 1 to 2, or in terms of atoms, 1 to 4. See that? 1 to 4 in terms of the atom count. Look what we have over here. 1 to 4. What do we have here? 1 to 4. 1 to 4. See? And so you have this issue coming up where you don't know if you have a whole mole of this or 1/2 a mole where each molecule is made up of twice as much, or 1/3 of a mole where each component is made up of 3 times as much. So what we have when we decompose it and we come up with this is what's known as the empirical formula. The empirical formula tells us the ratio, see the definition in the book, a chemical formula that provides a simple whole number ratio for the atoms in a molecule. What is the relationship between all of the different atoms? So, using this example again, let's say that we are looking at CH4, C2H8, and C3H12. Okay. These are these, on this side, are they molecular formulas or empirical formulas? Well, one of the quickest way to tell the difference is if you look at it and there's a factor that goes into both of them, you know that it's molecular. Why? What would the empirical formula for this be, CH4? What's the simplest whole number ratio or relationship between the two? The same thing. I can't reduce my 1 anymore. So my molecular formula is CH4. My empirical formula would be CH4. The empirical formula and the molecular formula for CH4 are the same exact thing. There's no difference between the two. Now I have C2H8. What's the simplest whole number ratio, simplest whole number proportion between carbon and hydrogen in that molecule? It is again CH4. Why? For every 1, I have 4. 1 and 4. In this one, for every 1 I have 4, and this is actually how it's built. In this one, it's actually built with 2 and 8. But the simplest ratio between the two, 2 to 8 reduces down to 1 to 4. Remember we did stoichiometry, and if I said they were related to each other that are 2 to 8, you would say, well, that simplifies down to 1 to 4. 1 to 4. What's the relationship here? 1 to 4. Does it reduce any more? No, it doesn't. What about here? C3H12. That's 3 to 12. Can I simplify that at all?
1 to 4.
1 to 4, right. So the empirical formula is CH4 for all 3 of these molecules. The empirical formula is CH4. If I say I have an empirical formula, it's CH4, is that molecule methane? And the answer is not necessarily. Could be. Could be methane, because the molecular formula might actually be C1H4 or CH4, but not necessarily methane. What that means is in the lab, as I do certain experiments, they're going to break this thing down. You need to stand up, go ahead. As I go in the lab and I break this thing down to a 1 to 4 ratio, certain experiments are going to tell me not exactly how the molecule is made, but it's going to tell me, in the end, your relationship between your products are this to this. You've got 1 to 4, you've got 2 to 7, you've got 8 to 13, you've got some whole number ratio between the two. And it doesn't tell you that it's that number exactly, it just says whatever it is, they relate to each other in this way. In the case here, they relate to each other in a 1 to 4 relationship. And so do these. I do the same experiment with a different molecule. It tells me carbon and hydrogen relate to each other with a 1 to 4 relationship. But my actual molecule is this. And then I do it with a third molecule. It tells me again, a third time, it's a 1 to 4 relationship between carbon and hydrogen. But I find out later on that actually what I was breaking down was this molecule. Okay? So the empirical formula tells you all of the atoms that are in the molecule and how they're related to one another proportionally. The molecular formula tells you exactly how many of each you need to build that molecule. Okay? We're going to use this concept as we press on through the end of the module. But the numbers aren't always going to be nice and easy 1s and 4s, are they? It's not going to be, you just happen to have 12 grams of carbon, and you just happen to have 4.04 grams of hydrogen. So that right there, they lay it out for you nice and simple so that you get the principle. Then we apply the principle and we get more difficult numbers. That's why we're doing stoichiometry. It's a nice 1 to 2 relationship or 2 to 1 relationship using nice whole numbers until you take baby steps to get to the point where you get these crazy numbers. You're like, where in the world does this come from? It came from real life, okay? Real life is not usually nice and simple, whole multiples and all that kind of stuff. But until you learn the principle of how to do it, they kind of baby step you into it by giving you nice, whole, proportional, easy numbers. They don't do that for long, but they do it for a while. Let's go ahead and take a look at example 8 and 9 then, because again, this is another teaching of the same material in a slightly different way. I'm going to leave molecular and empirical up there, because I think I might use it again in just a moment, but we will see. Let's see. The molecular formula for 3 compounds are listed below. So it's C4H12, molecular C4H12. Na2S2O 8. Cr2O7. What's that? K2Cr2O7. Potassium dichromate. Good. Okay, so we have C4H12, Na2S2O8, and K2Cr2O7. The question is, determine the empirical formula for each of those molecules. What am I going to do? I'm going to look at the subscripts. Remember that no subscript is an implied one. I'm going to look at the subscripts and see if there is a common factor that I can use to reduce those numbers. Okay? So, 4 carbons and 12 hydrogens. Okay. Good. So Ray's suggesting that the commonality there is the factor 4. And I can reduce the 4 to a 1 if I divide everything by 4. The relationship, maybe it's easier to see it this way, 4 to 12 can be reduced down to 1 to 3. Okay? 4 to 12 becomes 1 to 3. Correct. So the empirical formula for C4H12 is CH3. If I do experiments in the lab and I decompose the molecule, what I'm going to find out in the lab is I have 1 carbon for every 3 hydrogens. But I don't know what the actual formula for the molecule is. It could be CH3, it could be C2H6, it could be C3H9, it could be C4H12, boom, that's what we had, but it also could be C5H15, it could be C6H18. It could be multiples of 1 to 3. If all I know is the empirical, it's a relationship of 1 to 3. There's more information we need to determine which one of those options it actually is. You guys sleep a lot more than he does. So, Will, one more time. You need to stand up, do it. Second one, looking over at him and laughing at him because he's fallen asleep is like me throwing markers at Russell, Miss Russell, all morning, okay? So, you look up here, don't worry about him. Stand up if you have to. Let's look at the second one. The subscripts are 2 to 2 to 8, right? Common factor between those? Well, of course, if they're all even, 2 is a common factor, right? So we know we can go through and reduce those all by 2. And since 2 is also one of the factors we're looking at, we can't reduce it by more than 2 because we don't want to go less than 1. So it's 2 to 2 to 8. They're all even, so we can reduce it by 2. And it becomes NaSO4. So my empirical is NaSO4. My molecular, in this case, was Na2S2O8. What are the possible options for the empirical? Or what are the possible options for the molecular if NaSO4 is our empirical? Well, it could be NaSO4, right? This molecule, if the empirical is NaSO4, it could be actually NaSO4. That would be a multiple of 1. Multiple of 2, Na2S2O8. Multiple of 3, Na3S3O12. 4, Na4S4O16. Those are all possibilities using the same empirical of NaSO4. Lastly, K2Cr2O7, potassium dichromate. Are there any common factors in the subscripts? So, what's the empirical? It's the same thing. What does that mean? Well, that means that if this is what I come up with in the lab as the empirical, this is the first option for the molecular. It could be, and because we see the polyatomic ion dichromate, we need to work with that too. But theoretically, it could be K4CR4O14. It could be K3CR3O21. It could be K4CR4O28. Could be. But what is it actually? It's this molecule right here. So this one will give you the options of what it could be. This times 1, times 2, times 3, times 4, whatever. And when I say times 4, I mean the subscripts, to build different molecules with the empirical. The molecular, we're going to need more information. The molecular says, hey, I probably came up with this in the lab as the empirical, and more information let me know that of all the options over here, this was the right one. Okay. So is there any question between what's the difference between the empirical and the molecular molecule? No? Again, the short way to remember this is the empirical is one possibility. The actual is going to be a multiple of the possibilities. It could be the same molecule. In this case, it could be the same molecule. But it's not necessarily the same molecule. It may be a multiple of the empirical. Let's go ahead and do 8, 9 together right now, just looking at it. You don't need to write much down if you understand that concept. On your own, 8, 9 on the middle of page 299. Which of the following molecular formulas are also empirical formulas? And if it's not the empirical formula, write it. Write the empirical formula. So, first one. Al609. Is that an empirical or molecular formula?
Yeah.
So molecular, you know that because it can be simplified, right? It can be reduced down to a simpler whole number relationship between the two component elements. So what is the greatest common factor between these two? 3, which reduces the empirical to become Al2O3. So this is, again, I'll write this up here, molecular, empirical. If the molecular is Al609, the empirical is Al2O3. And again, in the lab, when I decompose whatever molecule it is, and I come up with the relationship between the aluminum and the oxygen as being a 2 to 3 relationship, it could be this molecule, but it could also be Al4O6, it could be Al609, it could be Al8012, and so on. We don't know yet. We need more information. In this case, we know that it happens to be this one that provides that empirical. The second one, PbO2. What's the empirical for that molecule?
It's the same thing.
Same thing. So in this case, PbO2 is the empirical and happens to be the molecular. MgCO2, magnesium. Same thing, right. I'm just going to write that arrow. Same thing. Okay? C8, 8HT, H18, O2. So they're all even, so the guess is that we could at least do by 2. Okay. If we do it by 2, we have C4, H9, O. Okay. Now look across and see if you have any 1s, or you have any, things that don't have common factors. The fact that there's only one of this means I'm done. Okay. But I would look at the other subscripts as well, if it were not a 1, and say, is there another factor that I can reduce that by to see if I hadn't gone far enough? Si3, H9O2. So Mr. Joda said it's the same thing. Do you agree?
Yes.
Okay, because we can't reduce, there's no common factor there, right? That we can reduce it by. So it stays.
I'm going to actually be able to tap numbers with this election.
Let's wait till we get there.
Okay. So we'll have to divide our numbers by units.
Sorry?
Will we have to divide our numbers by units? Is that right?
Don't worry about it right now. Just understand what we've covered. Just don't press too fast. So. Let's take a look then as we continue. Go ahead and take a look at 810. Objective was to get through the bottom of 899 today, but let's go ahead and look at, or excuse me, 299 today, but let's take a look at 810 and see if we can start to break this down a little bit more. Okay. So molecules' empirical formula is determined by experiment to be CH2O. When you, yes sir, you may. I'm sure you can, so that's why I just said yes, you can. Okay. A compound's empirical formula is determined to be CH2O. Real quickly, what are the, within the realm of possibility, let's just do a few. What are the, if it's empirical as CH2O, what might we actually be looking at? Well, we might be looking at CH2O, right? It might actually be that, its molecular formula might be that, but its empirical formula is this. What else might its molecular formula be?
C2H4O2.
Correct, C2H4O2. It could be C3H12O3. It could be C4H16O4. It could be C5H20O5, right? And so on. We don't know exactly what it is, but it could be It could be one of these molecules. Its molecular formula could be one of these, because they all have the same empirical formula as this. These all reduce it down to, is that right?
I thought it was 1 and 2, not 1 and 4.
That would be 6.
Yeah.
Yeah, you're right. That threw it all off right there. That makes, okay, so 2, 4, 6, 8, 10. There we go. So to go by force. All right, so CH2O, C2H4O2, C3H6O3, C4H8O4, C5H10O5, and so on. These are what it could be in actuality. This could be its molecular formula. All of these have the same empirical formula of CH2O. When we do those experiments in the lab, we're not going to know which one of these we have with certain experiments, but those experiments will tell us whatever it is, it's coming out in a proportion of 1 to 2 to 1. So it could be any of these, because it's some multiple of this empirical formula, CH2O. In a separate experiment, remember I said before, unless you have more information, this is all you know, which means it could be one of these. So in a separate experiment, it tells us, okay, there's another kind of information we're going to get now that's going to supplement what we understand over here to help us figure out what we're actually looking at. In a separate experiment, the molecule's mass was determined to be 180.1 AMU. That molecule, whatever it is, and sometimes, to be honest, I'll put an E out here and just circle it to remind me that's the empirical. Okay. Remind myself that's the empirical formula. I'm not dealing with the molecular formula, it's an empirical formula. But whatever it actually is, it's always going to be a proportion of 1 to 2 to 1. Okay? And I know that the mass of the molecule, whatever it is 180.1 AMU. What is the compound's actual molecular formula? If I told you that I had a molecule, and this is exactly what we are asking, we're telling you. You have a molecule that's made up of carbons and hydrogens and oxygens in that relationship, in those proportions, and whatever it is, it has a mass of 180.1 AMUs. How might you start to figure out what it actually is? Let's look at our empirical molecule. Again, it's CH2O. What would be the molecular mass of that molecule, my empirical molecule? So carbon has carbon. If I had one CH2O molecule, what would its mass be? Well, carbon is 12. Hydrogen is 1.01. And oxygen, we have two of them, right? And oxygen is 16. Because of precision, we're going to leave it at this. So, the molecular mass of this molecule, my empirical molecule, is 30 grams per mole or 30 AMUs per molecule, right? So one of my empiricals is 30 AMU. The molecule I actually have is 180.1 AMU. How many of these molecules are in this molecule? If one of them is 30, how many are in this one? 6 of them, right? You see that? If my empirical has a mass of 30 and my actual has a mass of 180, there are 6 of my empiricals built into my actual. And if my formula for my empirical is CH2O, that's my empirical, then my molecular is 6 times as big, which means it's a C6H12O6 molecule. Why? Whatever it is actually has a mass of 180. Its empirical has a mass of 30. How many empiricals go into the actual? 6. There are 6, the components that make up my empirical, there are 6 times of each element. How do I write that? I take each subscript and I multiply it by how many I actually have. I have 6 of the 1, I have 6 of the 2, and I have 6 of the 1. Just check it real quick. What is the empirical formula for this molecular? CH2O. Okay, again, this one, empirical, has a mass of 30 AMU. This has a mass of 180.1 AMU, which is equal to 30 times 6. So there's going to be sometimes here we're 1/10 of AMU off. That's all based on roundings. Remember over here we had to drop because of, it's built into that number over here. So if you get an answer that says it's 5.997, and the question says, is it 5 times or 6 times? The answer is 6. Okay? It's going to get you really, really close to a whole number, but it has to be a whole number. Remember, we learned that like the second module. They've got to be in whole number proportions, whole number relationships. So the deal is to be able to figure out the empirical formula. Given the mass of the empirical, given the mass of the actual, figure out how many times the empirical would fit into, maybe that's one way to think of it. How many empiricals could you fit into the actual? In this case, we could take, the empirical is 30 grams. 6 of them gives us 180 grams. So I take my empirical formula and I multiply every subscript by that number. In this case, it's 6. I take every subscript and I multiply it by 6. So if I go to the lab and I take this C6H12O6 molecule, I do experiments on it, and I decompose it, and I collect the products of the decomposition, they're going to come out in a relationship of 1 to 2 to 1. 1 carbon to 2 hydrogens to 1 oxygen. See, that would be our next option over here. C6H12O6, C7H14O7. If you were to go through, since these are all the possible molecules this could be, if you were to go through and compute, you could go through and compute the mass of every one of these, which would be basically 30, 60, 90, 120, 150, 180, 210. You go, oh, there it is. Why? This molecule has the same mass as my unknown. It has the same empirical formula as my unknown.